Hey everybody, my name is Paul Abernathy and welcome to another episode of Master the NEC, sponsored by Electrical Code Academy. Now on today's episode, we're going to do motor circuit basics, and we're going to talk about single-phase motors in this series. Now, we're going to have a series on three-phase, and we're going to get into some of the more complicated calculations. But when you're preparing for an exam as part of this exam prep series, you need to understand the basics. And so we're going to go over the basics. This would be sizing overloads based on the National Electrical Code. And we're going to talk about sizing the short circuit ground fault protection for that circuit. And we're going to talk about sizing the conductors and what have you. We're going to talk a little bit about what's the difference between the FLC and FLA, which sometimes they might call it the FLC in the code, but what they're talking about when it comes, for example, overloads, they're really talking about the FLA, which is what's on the nameplate. And we'll cover all that. We'll talk about what tables within the NEC that you're going to need to use, which would be, for example, to find the FLC for the various types of motors. And this is going to be back in the back part of Article 430 when dealing with motors. And so that'll be the 248 table, 250 table, and what have you. And we'll look at all that. So the first things first, we want to explain a couple things about taking your exam when it comes to motors. Now, when you're going through your exam, and if you haven't watched our navigation series on preparing for your exam, you're going to understand that you go through the exam and you're going to answer the questions that you know, and you're going to mark the ones that you spend more than a minute trying to answer. You mark them so that you can come back later. All of the calculations that you get to, you're going to simply mark right away unless you just know the answer by looking at it. And just something you've seen in another exam prep or whatnot. And you're going to cover those later. But the key thing is you want to go through the exam and get the things that you know right away. If there's something that takes you a little time and your question, go ahead and mark it, because what you're trying to do is cover the exam in different waves so that you're actually building in time. Because the biggest thing that people find about taking an exam that's problemsome for them is they run out of time. And it's really taking an exam, it's something called time management. And that's the most important thing. You really have to know how to budget your time. So if you go through and you answer things like something you just know, some question maybe about receptacle placements in 210.52, and you just know this because you're used to it, answer that question. Go with your gut. A lot of times people will answer something they don't know. They'll come back and they'll change their answer. If you know it right away, hey, you either are ready or you're not for the exam. So mark it, move on. If there's something that's going to take you over a minute, because typically you get about 2 minutes a question when it comes to the total volume of questions on an exam in the hours. And of course, that's going to vary depending on state to state. But you want to mark it, and you want to come back on the second wave of your question. And then you want to come back on a third wave, and that's when you're going to really focus on the calculations. Now, of your calculations, some exams are two-part, so you really have to focus on your navigation and how to find things in the code. But then you have the calculation in which you're actually going to have to try to answer all the calculations. Okay, so in this series here, we're just simply going to talk about the basics. We're not going to get too deep into other things like torquing motors, because typically on an exam, they're not going to get too deep. Okay, it's not to say that they won't on every exam, but majority of it, they want to test your understanding of things like how to size the short circuit ground fault protection in 430.52. They want to know that you know how to size the feeder conductors in 430.24. They wanted to know if you understand the limitations when it comes to the tap conductors from a feeder for motors in 430.28, things like that. And so they want to make sure that you understand those basics, and they give you certain information. Now, most of they're not going to give you things like power factor issues. They're not going to give you efficiency issues. Now, there might be an efficiency question, and that's covered in our basic like Ohm's law and calculation basics class. But they're typically not going to conjunction that with a motor calculation. And usually they're not going to give voltage drop, because then it's different calculations. It's too many equations for the time. That's not to say some states aren't different, but most of them, if they're following some kind of formality like a PSI or some kind of testing system, they're really straightforward questions, and they're not there to trick you. but you've got to really stop and read the question. I posted some graphics on LinkedIn, and it was amazing the number of responses I get. And I would say probably 85% of the responses were incorrect on these basic calculations. So it was kind of shocking to me. I thought they would be pretty simple. And it seemed to me that it was engineers wanted to overthink it. And electricians, for the most part, got it right, and some that got it wrong were apprentices and they're learning. But it seems like when it comes to an exam, and that's basically what I deal with, preparing you for exams and teaching you the basics. And then we have an advanced series where we can go into things like ambient temperature changes and whatever. But this is to help you pass the exam. This is part of the exam prep series. So let's get right into it so that we can kind of understand. I kind of gave you the overview of it. So what I want to do is go straight into the code, the PowerPoint presentation, and let's kind of start covering the basics, if you will. All right, so we go to the PowerPoint presentation, and here you're going to see that we have these branch circuits coming out to this motor here, and what you've got the motor down here, which this is a single phase. Okay, so we know we're dealing with that, and usually the exam is going to give you that. If you didn't know that, you could tell by the voltage. This is 230 volts, so it's 5 horsepower, so it's single phase. And what we've got here is the actual short circuit ground fault protection here, and then we have the overload protection here. Now, some motors, it could be integrated into the motor, but we're teaching you how to calculate independently the motor application here. Okay, so it's not integral. Thermal protection is not integral to the motor. It's separate right here. Okay, we're just trying to cover the basics here. We can't cover everything in every video, so we're just trying to stick with that. So what we're going to learn, so this is a basic circuit. There's no feeder involved. This is the branch circuit coming out. You're hitting the disconnect here, which is going to offer the ground fault protection and short circuit protection. And remember, this is providing ground fault and short circuit protection. It is not providing overload protection. That is being provided here, okay, in the overload itself, okay? And so again, and we have the conductors that come through straight down into the line side and then out of the load side down and into the actual motor itself. So what we want to understand is how to size these variables here. So let's do things. Let's do the things first. Let's go on and size the conductors. All right. So the conductors that we're dealing with here. All right. So when we're sizing conductors, the code tells us that we need to look at 430.22a. All right. So let's go to the NEC and go to 430.22a. So in 430.22, first of all, it says this right here. It says conductors that supply a single motor used in a continuous duty application, and most motors are continuous duty, and on exam they'll say they're continuous duty, or you assume they're continuous duty unless they say something otherwise like intermittent duty or whatnot. So it's continuous duty, and it says that those single motor those conductors shall have an ampacity of not less than 125% of the full load current rating as determined in 430.6A1 and not less than specified in 430.22A through G. Okay, so just so you have an application where it's other than continuous duty, but ours is dealing with continuous duty. And so in that application here, we're going with the basic rule here because we're not dealing with a direct current motor rectified supplied. We're not dealing with any of that. We're not dealing with other than continuous duty, which if you did, you'd simply follow these rules here. Okay. And we're simply dealing with the fact that we're dealing with the continuous duty motor, and it's 125% of the FLC. Okay. Now let's come back to me real quick. So FLC, full load current. Now the value that you're going to see on the nameplate of the motor, the amps that's there, is full load amps. Now sometimes again in the code they might refer to that as the full load current, but if you see it underneath the section in the code part 3, which is dealing with overloads of 430, then you know that that's specifically dealing with the nameplate ampacity. Okay. All right. So let's go and look at what we're doing. So let's go look at that table. And remember, we're dealing with a 5 horsepower, 230 volt motor, because that's what's on the graphic and that's what's going to be on your exam question. Okay. So let's go back to the NEC. And we're going to continue down, and I could search it, but I want to show you stuff as I go along. Remember I said part 3 right here? That's dealing with overload. Remember that. That'd be a good point to make a flashcard if you're going to study 430 and you really want to hone your navigation skills in 430. Then you remember there's another audio podcast that I do which explains how to create flashcards and that might be one of your flashcards that you create. All right, so what I'm going to do is I'm going to go in and search and go to 430.248. And let's just kind of let it go down through these to there. Okay, so what you see here, and let me get it on the screen and I'll get rid of this right now. And we'll do it a little bigger so you can see it. All right, so what we've got here is full load currents in amperes for single phase alternating current motors. Okay. Now it says the following values of full load currents are for motors running at usual speeds and motors with normal torque characteristics. Okay. It says the values listed are rated motor voltages. The currents listed shall be permitted for the system voltage rating 110, 120. So these are your nominals, but these are the ratings that actually are going to be on your actual motor itself. So if you ever saw a 240 volt circuit nominal for calculation purposes, when you're dealing with the motor itself, you go with the voltage rating that's on the motor and you'll see that it's a 230 volt. Now sometimes you'll see a 115/230 depending on how you wire up the motor. Okay, so here is a 230 volt and we're dealing with a 5 horsepower, which is right here. So this is the values we're dealing with. Now in our case, it's 28 amps is the FLC. All right, so let's kind of go back to our graphic, PowerPoint. So in this case right here, is 28 amps is the FLC. Okay, so you would write that down. Well, there's 28 amps here. Okay, so in that case, it's stated in 430.22a, okay, that we wanted to have that the conductors had to be no less than 125%. All right, so you get your calculator out, I should have put the calculator on the screen, but we'll just do the calculation. So it's 28 times 1.25, and that is 35 amperes. All right. It's 35. So let's come back to me. Okay, so the 28 amps times 1.25 is 35 amps. So I need a conductor that's rated for 35 amperes. So here's the neat thing. So back in the tables that you looked at when it comes to ampacities, 310, 15, B16, you had these little asterisks for smaller conductors. Well, when it comes to, and then that's going to send you to 240.6 and those type of things. And just remember with motors, you have an allowance for the conductors to be sized a little bit smaller than what you might see for the short circuit and ground fault protection device. So that's not going to line up. So the traditional rules of protecting, for example, a 10 gauge wire at 30 amps is not going to apply to motors. Okay, it's very common to have the short circuit and ground fault protection to be where typically you'd have a 30 amp overcurrent device protecting a 10 gauge. Well, you might have something as large as a 50 amp overcurrent protective device providing that short circuit and ground fault protection, actually protecting a 10 gauge. It's very common. Okay, so let's go on and select the conductor and we'll kind of work our way through that. If you're not familiar with how that works, let's kind of do that. So let's go back to the code. And in the code, we're going to want to go at this point, I want to go to 310.15b16. So we're going to go it. Now again, we're doing this just like you would follow along in your code book. Let's go to 310.15b16. And here's where we're at. Now, a couple things that I want to remind you here. First of all, we're looking for a conductor that has 35 amperes. Well, if I was dealing with let's bring it back because there's some other things that you got to really keep in mind. Terminal limitations. Motors generally have terminals that are rated at 75 degrees C. And that's pretty standard for the motor terminals. However, you got to be real careful about the overcurrent devices that you're connecting to. If they're listed for 60, and most of the day are going to be 60/75, then if they were only rated 60, then 60 is your weakest link. And so you would have to focus on the 60-degree column for your ampacities. That's the terminal limitations in 110.14. So don't forget those basic rules that we talk about in other episodes that we teach you for exam prep. Remember, terminal limitations are key. It's the weakest link concept. Now, if I was dealing with a motor with 75-degree terminals, and I had a 75-degree rated circuit breaker, let's say, and I had 75-degree rated terminals on the motor, but the wire was rated a TW, for example. Now, TW is limited to 60 degrees in 310/15B16. That is the weakest link. So I'm going to be focused on the 60-degree column. It's real important that you understand the basics of 110.14C. And understanding that if your conductors are smaller than 1, then you're going to deal in 60 amp values. Okay. If you're dealing in under 100 amps, you're going to deal in the 60-degree column concepts. And I really urge you to go back and look at that video or that episode that we did dealing with terminal limitations and how you deal with that. And when they're over 1, then you're going to deal with the fact that it's going to be 75 degree, and it's all depending on what you have in front of you. If you give an exam question and they don't tell you the terminals, don't assume anything, okay? If none of the terminals are listed, then you're going to, and you know that what the size of the conductors are, and you know what the ampacity is that we're dealing with, then you're going to default to the 60. If you know that it's over 100 amps, then you're going to default to the 75. Okay, some of those things that you have to keep in mind. Again, go back and watch that on 110.14C and understand terminal limitations, and watch our other video in the exam prep series where we talk about terminal limitations and adjustment and corrections and things like that. All right, so let's get back kind of to the graphic here. In our case, we are dealing with, let's say it was, we're just going to do some exam prep questions now. We're going to assume that it's THHN. Okay. Now, on your exam, don't assume. If they don't tell you the conductor type, then because of the ampacities we're dealing with, you're going to default to the 60-degree column. Okay. You're not going to assume the motors are 75 degree, even though that's pretty common. You really want to focus on what's on the exam question. So when I tell you, stop, analyze the question. The answers are usually in the question. You just have to analyze it. Okay. So I'm really trying to get you to slow down. Okay. All right. Let's go back to the code. All right, so when you look at the code here, if we didn't know the terminals and we didn't know what the wire, but we knew what the amps are, which is 35 amps, then we're going to be in the 60-degree column. And that's significant because it could require a 8 gauge for that application. But in our case, we told you the terminals. If you go back to the graphic, now let's kind of go back to the PowerPoint, you see that we told you the terminals are 75. Okay, and then we'll tell you that the terminals at the breaker is 75C. Okay, so we kind of gave you all the variables here. And so most of the time, the conductors you're going to use traditionally are going to be THHN, THWN-2, XHHW-2, and all these type of things. But just be conscious of that. Here we just tried to give you some information to tell you terminal 75, everything's 75. But the point is, if I used a wire method, so think on the exam, it gave you 75 terminals, but then it told you to use TW wire in the question. That's kind of not a trick question. That's just trying to say, hey, this wire is only good for 60-degree column in 310/15B16. Got to think about those things. All right. Weakest link. All right, let's go back to the code. All right, so when we look at the code, we see in our case, let's assume that it's one of these wiring methods. Okay. One of these wire types, I should say. RHW, THHW, THHN. Okay, so it would be 35 amps. Now, keep in mind that the code also tells us in 110.14C that I could use one of these with a higher ampacity, temperature value, in other words. But, and it does have a higher ampacity for adjustment and corrections where applicable. But since our terminals are limited to 75, we still can't exceed the terminal listing value here. And we have to make sure our load doesn't exceed it. In our case, the load doesn't exceed it, but we need a conductor that can handle that. So here's what we've got. All right. Now, the actual load, just so you know, the actual load is just 28 amps. I mean, that is the load. Okay, and that's covered all in our adjustment and correction series, and hopefully you watch that video. But in this one, you know, we're trying to size a conductor, and the code's telling us in 430.22 that we're going to size it 125% of the FLC, and that's what we've done. So in our example, let's kind of go back again to the code. What we've done here is we're choosing a 10 gauge, and that's what we've chosen. All right, so let's kind of go back to the presentation here. All right, so this conductor here would be a 10 gauge based on a 5 horsepower, 230 volt motor. Okay, and that's the conductors you would have here. Okay, now let's move on. So we know the size of the conductor, and again, we're talking about a basic motor. We're not talking about anything else. I'll only give you advice here if we go back to the code, because I like to cover all aspects. Unlike some preparation courses, I like to cover all of the basics. Okay, so we want to go to 430.22 again. And again, it makes my videos long sometimes, but I truly want to help you. Oh, let's stop right here real quick. So when you get to the beginning of 430, this can be a game changer for you. You see this little table here? This allows you to jump into the most significant areas of the code instantly to maybe answer your questions. So if I was looking at a calculation for exam prep, okay, and I wanted to know how to size the feeder, then it would, 430.22, it's part 2. If I want to know how to size the motor short circuit and ground fault protection, I'm going to use part 4 or part 2, depending on what I'm dealing with. I can do the MOCATs, the motor circuit conductors are going to be found in part 2. All those type things are going to found thermal protection, part 3. So this kind of gives you a quick jump. If I need to do the motor feeder short circuit and ground fault protection, it's part 5. So, and we'll cover those. But this is good. If it asks you a question about the motor's disconnection means, then you've got that part right there. So look, this is a good roadmap for you to instantly jump if you're just not sure where to go. Okay? If you're just not sure, this is going to give you some good guidance on that. Now remember, you do have adjustment and corrections that will take place if you have ambient temperatures wherever those conductors are running, or if you have more than 3 current carrying conductors in a raceway and all that. Because again, 430.6 reminds you that, you selected the allowable ampacity tables in accordance with 310.15b, and all of that takes place, and you have to keep that in mind. So just a reminder, okay? Don't discount your other training that we've done in this series. All right, we're going to keep. All right, so here we go. Single motor. So that's what we sized it. We've determined it's a continuous duty motor in our example here, and 125% of the full load current, and that's what we've done. All right, so now let's move on. All right, so we're back to the presentation. Now, let's size this short circuit ground fault protection that's required. Again, remembering the 75° C lux. Now, here we're going to use table 430.52 and the rules that are in 430.52 to size this here. Now, in our case, we're going to say that that's an inverse time circuit breaker. Okay, so it's inversely proportional. So the higher the current, the quicker the trip. All right, so that's the concept here when it comes to this. So it allows that current to skyrocket in a situation of a short circuit and ground fault, which results in a quicker clearing time of this device. Okay, now this could be fuses, and you're going to see that that percentage is different. But for our calculations, we're going to stick to a circuit breaker. All right. Now there are occasions where you might have a fuse that's not going to have an overload, because it might, or even a fuse, depending on the size of the motor, that it might incorporate the overload and short circuit and ground fault protection all in one device. But in our case, we're going to show you how to size both. We can't cover everything. This is funny right here. It looks like I forgot to connect these two together. I always notice something in the graphics that I do. But anyway, you get the gist, right? All right, so let's size this one. So in the code, let's go to 430.52. And let's see if we can determine what this short circuit and ground fault protection needs to be. Now remember, we already found out what the FLC was, and we're going to need that here. And it was based on 28 amps because that's what the FLC was for the single phase 5 horsepower 230 volt rated motor. Okay. All right, so let's go to the code and let's go to 430.52, see what we're dealing with. All right, so let's type in 430.52. Now you'll have a tab for this if you buy tabs, because the tabs will have a tab for that because it's a very common table used in the calculation of motor circuits. All right, so here we're at. So 430.52, this is not the table. This is just the general rules right here. And it's saying general. It says the motor branch circuit, short circuit, and ground fault protective device shall comply with 430.52B and either 430.52C or D as applicable. Okay, so what does B mean? Well, B says, all right, this is dealing with all motors. It says the motor branch circuit, short circuit, and ground fault protective device shall be capable of carrying the starting current of the motor. Okay, so that's a key role here. So let's come back to me. So in a motor, you have a certain amount of startup and you have that sudden surge. And so we're going to take that into account when we're doing all this sizing in the motors. And that's kind of taken into account when you deal with the applications of the sizing of the overcurrent device and the short circuit and ground fault protection. And of course, we also cover that in the overload when we're doing the overload, because we're going to oversize that as well, whether it's 115% of the FLA or higher, up to 140 if it doesn't hold. So there's different aspects and conditions, and we'll kind of look at that. And we have some conditions that are in our graphics that we're going to follow. Let's go back to the PowerPoint. All right, so what we're doing here is we're going to size this right now based on what the FLC is here. And that's how you start. So let's go back to the code. All right, so it says also C or D. Well, C is right here, and then D is, and you have some, for instantaneous, which we're not dealing with in this example. Okay, and then you have multi-speed motors, and then you have torque motors. Okay, now we're dealing with what we would consider standard non-torque motors or non-high torque motors. We're just talking standard motors because we're trying to prepare you for exam. I don't want to get you confused into more than just the standard details that you're going to need for your exam preparation. Okay, we're not here to try to make this overly complicated. All right, so it says C or D. Well, C. It says in accordance with table 430.52, which is the other aspect. So we've got the first requirement to make sure that it can actually capable of carrying the starting current. And second, we have a protected device has a rating or setting not exceeding the value calculated according to the values given in table 430.52 shall be used. I will remind you that there is an exception. And the reason I'm telling you this is this is the one that's mainly used. Is that it's this right here. And it says, okay, look, let's assume that we're going to use this table. It says where the values for branch circuit, short circuit, and ground fault protection devices identified in table 430.52 do not correspond to the standard size rating of fuse, non-adjustable circuit breaker, thermal protective device, or possible settings on an adjustable circuit breaker, a higher size rating and possible setting that does not exceed the next higher standard rating shall be permitted. Okay, so this basically is something that you need to consider as like the next size up rule when it comes to the overcurrent device, or the protective device, I should say. So if it doesn't correspond to it, you're going to do that. Now, if the question had an exception and it says don't apply the exceptions, then remember that you can exceed, okay, the values that are going to be given to you in 430.52. Okay, for example, a inverse time circuit breaker is going to be 250%. You couldn't exceed it. So if the value ended up being, say, 42 amperes, you couldn't go to the next size up if it doesn't correspond with the table in 240.6a, which is going to give you a list of overcurrent devices, a standard overcurrent device. Then you can't go up. So that's important. Look for the exceptions. Now, if the test says all exceptions not considered unless stated, okay, then you know that then the exceptions aren't there. So you have to look at the wording and to make sure. So stop and take your time and read all the information. If the exceptions are, if their exceptions don't apply, then you would have to go down to 40, okay, because you can't exceed the 250%. Okay, so that's a little nuance to be aware of. If it look for the words or whether or not it accepts something, or if it doesn't and it allows the exceptions, or if the test says all exceptions considered, or if the question says exceptions considered, then you use the exceptions. And this would allow you to go from, let's say, the 42 point whatever amps is what you calculated, 250%, let's say, of the inverse time circuit breaker. It would allow you to go up to the next size over the 40 would be the 45. And 45 amp device can protect the 42 amps in that aspect. So important to look at those exceptions when you're taking exams. Stop and read the words, okay? Don't get lost in it, okay? Make sure you read it. All right, let's go back to the equation, to the graphic. All right, so in this case right here, we need to size it. So let's go back to the code. And the code is going to tell us that we're going to use the values in that. Now, just to cover the other exceptions here, your exception 2, it says, where the rating specified in 430.52 or the ratings modified by this exception is not sufficient for the starting current. Remember, the item B here said it's got to be sufficient to carry it during the start. Then you have some other allowances down here to be considered. So it's, so you could, the rating of the non-time delay fuses not exceeding 600 amperes or a time delay class CC fuse shall be permitted to be increased, but shall in no case exceed 400% of the full load current. So we really don't have to go into all these details, okay? You just need to know that the basic rule is going to be follow the table. Unless there is some condition that it states in there, like it can handle the starting current, and then it gives you these variables, or it asks you about fuses. So once you get here, look at the question and then determine whether any of the exceptions are going to apply or whether or not the question doesn't allow you to apply the exceptions. Many times it's exam questions don't get so far down into the weeds because it can really bring in different variables that the test question didn't account for. And you're not expected to understand that. So don't worry about it. Don't get pressed in it. Just really read the question and focus. And we're covering a lot of really good detail here. But I want you to understand those exceptions are there. We're not going to cover every single one of them. Just know the basic rule, follow the table, and we're going to look at the table. But there are exceptions if the question brings up some condition. So remember, it's got to handle the starting current. If there's a statement in there in the question that triggers your response to use the exception, like it can handle the starting current or all this, then you have to think about these exceptions. And I just want them to be in your mind when your for your exam prep. All right, let's go back to the code. All right, so now let's go on and allude to this table. And of course, you have the second one that says overload relay table. The maximum branch circuit and ground fault protection ratings are shown in the manufacturer's overload rating table for use with a motor controller. And you got some aspects here. And then, of course, if you're dealing with the instantaneous trip circuit breaker, then an instantaneous trip circuit breaker shall be used only if adjustable and if part of a listed combination motor controller having coordinated motor overload and circuit and ground fault protection in each conductor. And the settings is adjustable to no more than value specified. So this is one where they're built in. They have the instantaneous trip circuit breaker involved in it. It's a combination system with the motor controller. Okay, just slow down and see whether or not those applications apply. Okay, and then you have an exception to that right there. I'm not going to get into those in detail because very rarely do you ever have this one on an exam. Okay. All right, so now here's the table we're talking about. So here's the table. And notice that this table says maximum rating. Now, you have the exceptions that were afforded you. Okay, you just saw. Okay. Now, we're dealing in our exam questions with these. Inverse time breaker. You see a little note 2 here. Note is very much applicable. It's not an informational note, it's a note. And it just reminds you that the values given in the last column Also cover the ratings of non-adjustable inverse trip type circuit breakers that may be modified as in 430.52C1 exceptions. So just keep that in mind. But I can tell you right now, most of the time, you're simply going to pull to this table. They're not going to get too far down into the weeds. Okay. And if you wanted the video to teach you every single thing about motors, that's a more extensive course. And of course, we can do that. But really, we're trying to teach you the basics for exam prep. Okay. All right, back to the code. All right, so in our case, what were we dealing with? Well, we were dealing with a single-phase motor right here. And we were dealing with an inverse trip circuit breaker. So it's just this simple. You go, it's 250%. Now, it is 250%, and as it said, of the FLC, because that's what it said back here, all things considered in our test question, right here. All right. So what are we going to do? How are we going to deal with this, and how we're going to size it is basically what we're worried about here. Okay. All right. Now, how do we do this? Now, since we know, let's come back to me. Now we know that the FLC is 28 amps. We know that the percentage we're going to use, and we can't exceed that value unless an exception applies, and we got to note that overcurrent device, or that, I should say, ground fault protection and short circuit protection has to be, and remember, it's not overload, that's separate, has to be no more than a 250%. So we get our calculator out and we do the math. So I'm going to get my calculator, and I'm going to, I can't see. So let's do 28 times 2.50, and that is 70 amperes, okay? 70. All right, so the first thing that people say here is 70 amperes? But it was only a 10 gauge wire. Why can I do that? I feel worried about it. Remember, that is at 250%. That is to allow the startup. That's the short circuit, and ground fault protection at a fault condition is going to skyrocket, but it's not going to cause false tripping on a motor trying to start and run, and it's perfectly okay. And the code allows for this. Okay, so while you do have the values that are in the code in overcurrent protection in 240.4, and it gives you those for small conductor limitations. For example, it says that, and we're going to go look at that because I want you to be clear on that. We're covering everything here that we can do the basics of. So I want you to, because some of you might feel uncomfortable, and those that are not new to this go, Paul, move on. I'm not uncomfortable with it. I do it all the time. Yeah, but there's others out there, apprentices that are going to be learning that aren't, and we just want to reestablish that, especially the confidence when you're taking an exam. Again, this is exam prep. So let's go back to the code. All right, so we determined that we need a 70 amp device, and as it says, let's go down here. As it says here, that's the maximum rating. So first thing we have to do now, before an exception could even kick in, because I have nothing that says excluding exceptions, I have to make sure that I have a 70 amp device. So I'm going to do this, and I'm going to go to 240.6. And I'm going to go back to that. And I'm going to see if I do it. Let's keep on going. Here. Okay, so standard devices. Well, it just so happens that there is a 70 amp overcurrent device. And so I'm not exceeding. That's the device. So if you come back to the graphic or the presentation, what we've established so far is that this device, because we're talking about, in our case, we're going to use an inverse time circuit breaker, that this would be 70 amps. Now, what if we were going to do a, let's go back to 430.52. What if the question asked for a dual element? Let's go back, because I want to, let's jump back to it and let's look at one, because I want to make sure we cover everything. If there happen to be a case, my graphics usually don't show fuses, but I want to go back so we can do that. Okay, let's do it here. Let's see where we're at. Okay, you're still on the graphic. I want to bring it back to the code. And what if we were dealing with the question said a dual element time delay fuse? What if that was in your question? All right, so in this case, we're dealing still with the single phase motor. And incidentally, an AC polyphase motor is a three-phase motor, and we're going to cover that in the three-phase motor series. We're just dealing with the basics here on a single phase. So it would be 175. So it's exactly the same scenario as with the 250. You're just going to do that calculation. And let's do that calculation, and it's 175%. So let's do that. So it was 28 times 1.75, and that's 49 amps. Okay, 49 amps. So then we would go back to the code, and then we go back to 240.6 and see, well, what do we need for 49 amperes? All right, so we go back to the code, and we're going to go back to 240.6. Oops, went too far. All right, so here, and again, this is standard size for fuses and inverse time circuit breakers. Okay. Now, in our case here, and let's double check down here. Okay. In our case down here, we had 49 amperes. Well, doesn't correspond, so that I can put it on a 50 amp fuse, and it would be totally fine. Okay, again, we were just going to cover the basics here and keep it from getting overly complicated. It also need to read this, and I'll just tell you because it deals with the standard table, because you notice that this table is 240.6a, and it's new, which used to be a list. Now it's new as far as how they formatted this. And make sure I'm still on it. Yes, okay. So you go down here and just read it. So A says fuses and fixed trip circuit breakers. That's your standard circuit breaker. It says the standard ampere ratings for fuses and inverse time circuit breakers shall be considered as shown in table 240.6. Additional standard ampere ratings for fuses, so we have some in addition to those, and that would be 1, 3, 6, 10, and 601. Okay. The 601 is to allow for standardized sizing, even though it might be a larger fuse. It's standardized sizing for the whole fuse holders. It says the use of fuse and inverse time circuit breakers with non-standard ampere ratings shall be permitted. And what does that mean? Well, that means that you might have circuit breakers that are designed that aren't to the standard that's in that table. Okay, so you might have a gap, let's say, between, let's say, 60 and 70. I'm just using this example. And one manufacturer might actually make one that's rated for 65. So it would be in between. So you could use one, and instead of it being, if you wanted to use one that's more specific for it, then you could. But they're permitted. But you could go to the next size as long as you meet all the applicable rules in the exception. So just kind of telling you these are the standard. But there are other ones out there that are non-standard, and they're permitted. Okay, it shall be permitted to be used, not required. Shall be permitted to be used. You could just go with the standard that's listed here in the table. All right, so let's go back to the code now, because I want to show you that circuit rule, because there's still people out there, I can hear them, that say, I don't know that I feel comfortable with a 10 gauge on and we said 10 gauge copper. Also, assume copper unless it states otherwise to aluminum. Just always assume copper. Usually in the exam information will tell you some givens, like to assume copper, to this, that. If it wants you to use aluminum, it'll tell you that. Okay, so keep that in mind. Just little tips. So in our case now, some people don't feel comfortable that a 10 gauge, which is good. Traditionally, we're familiar with protecting that at 30 amperes. I mean, that's what we're all used to. And that's what that little asterisk is that's in that 31015B16, reminding us to that. They don't feel comfortable putting it on a 70 amp overcurrent device. It's okay. It's not a problem. And I'm going to show you why. All right, so now let's go back to the NEC. All right, so that's just to kind of give you that information there. Now, let's go on and go to what we're talking about for protection. All right, so remember when we talk about small conductor rules, and you see it here, and this is in, and I want to show you the general, the basic requirement here, is in 240.4, protection of conductors, okay? So that's what the real devices are there to do, to protect the conductors, okay? That's what 240 is all about. Now, indirectly, it might protect the motor because it trips or whatever, but in reality, the whole focus here is protect the wire, because that's what's in the walls, that's what's can overload and or have a short circuit ground fault protection if not sized right, could burn it up or cause something else to happen. Or so we're really trying to protect the conductors. Now, indirectly, we're protecting equipment, okay? And we have other rules. The overloads are there to protect the equipment, things like that, okay? So anyway, I just want to give you that kind of that basic. Now, here's the thing. This is the most important statement here to help you out. Conductors other than flexible cords, flexible cables, or fixture wires, which have their own protective requirements, shall be protected against overcurrent, which overcurrent, just to kind of give you an overview, overcurrent is accumulation of short circuit, ground fault, and overload. Altogether, we consider that overcurrent. Okay, so when you're taking an exam, you notice how when I go like this, my head looks huge? I can hear the comments on that now. People like, Paul's head's big again. All right, so now, sorry. Yeah, I had those moments. So, I almost lost the train of thought there for a second. So, you have to understand that when you have overcurrent, it's really encompassing short circuit, ground fault, and overload protection. But when we're talking about short circuit and ground fault protection, that's all we're talking about when we're protecting the circuits for the motor. It's the overload that's protecting the actual motor, as well as a component that does protect per circuits. But they're two different aspects of it. Now, could I incorporate a fuse that does it all? Sure. The code has provisions for that. Okay. But we're talking about two separate aspects here. So don't get it more confusing than it is. If any of that does confuse you, email me. People know me, I'll do little videos and anything to give you help, especially during our one-on-one sessions, during our exam prep. If you purchase our exam prep program, it comes with some one-on-one training that we conference call and video screen. Write those questions down and we will answer those. These are basics here that we're trying to cover for basic motors. All right, so let's go back to the code. All right, but the most important part we're going to get at is this. It says, and I'm going to read it again. It says conductors other than for flexible cords, flexible cables, and fixture wires shall be protected against overcurrent, and remember that's short circuit, ground fault, and overload, in accordance with their ampacities specified in 310.15. And again, that encompasses a lot of things in 310.15. It doesn't just say 310.15 B16, it's all of it. You have adjustment and corrections that might come into play. You have to take those things into account, okay? And then it says, unless otherwise permitted or required in 240.4A through G. All right, so let's look down. So the first rule that we're going to focus on, okay, is one thing to remember is when you're dealing with overcurrent devices rated 800 amperes or less, and all of these conditions can apply, then you can use the next size up. And we cover that in another series. Okay, that's what's basically, other than the exception, allowing you to go to the next size up rule. All right, but you still have to be aware of these basic rules. Most of our motor calculations for individual motors are not going to be more than 800 amps. Okay, so don't worry. You're going to have the next size up rule is going to be applicable, and you can do that. All right, so here's the one I want to focus. So you have the small conductor rule, and this is what everybody's usually familiar with. Okay, and it basically says you're going to make sure that you don't size the overcurrent protective devices larger than what is provided here for these conductor sizes. But it does go on and say, unless specifically permitted in 240.4E or G. Well, look at G. It says overcurrent protection for specific conductor applications. Overcurrent protection for specific conductors shall be permitted to be provided as referenced in 240.4G. And notice what you've got down here. You have right here, motor control circuits conductors. Okay. and it incorporates part 2, part 3, part 4, part 5, part 6, and part 7. All of these are going to allow you to modify, okay? Modify these small conductor rules here, okay? So traditionally, if I had a 10 copper, you remember that that's the little asterisk that's in 31015B16 that's going to send you right here at 240.4D to tell you, okay, it's only good for 30 amperes. Remember that. And I have to protect it at 30 amperes. Well, that's not the case because it modifies it right here. Okay. And then it gives you D1 through D7. So you have all these. Now, let me show you the one that we're talking about. As you get down through all of these, well, I guess I already showed you the one that we're talking about. So that's your general rule that we're talking about here, at least for right now, small conductors, and we're allowed to use G. And I just read G to you. And that's what allows us to jump over into part 2 and do what we just did, okay? And part 3 for overloads and everything else, okay? So that's what we did. All right, so let's get back to our graphic and continue sizing. All right, so we sized this. This was a 10. We sized this 50 amps. If it was a dual element fuse. In our case, we use an inverse time circuit breaker, so it's 70 amperes. So we have a 70 amp one, 70 amps, protecting a 10 gauge wire. It's perfectly okay. Now we want to size the overload in this single motor application. So in that case, we're going to look at 430.32a. So let's go to our code book, okay, and go to 430.32a. See what it says. All right, so I'm going to go here in your code book. You're going to go to 430.32, and we're going to keep going until we get to it. There. Okay, so what are we dealing with? We said that it's a continuous duty motor. That's most of the time what you're going to get at exam unless it states otherwise. If it states otherwise, you just simply follow the same principles, just follow the rules. And of course, in a more advanced class, we'll show you the other, and that's going to be our advanced motor calculations class. Really don't think it's that necessary for your exam because they don't get that detailed, but you might want to know, so we'll do it. But it's not going to be part of the exam prep series. All right, now, motors more than 1 horsepower. In our example, our motors were 5 horsepower, 230 volt, single phase. Okay, so that's what we're dealing with. So in this case, it says each motor used in a continuous duty application, and we're going to always assume our motors are continuous duty unless it states otherwise. And rated more than 1 horsepower shall be protected against overload by one of the means in 430.32A1 through A4. Okay, so A1 is, okay, so now we're just dealing with overloads. Now the first option is separate overload device, a separate overload device that is responsive to motor currents. Okay, this device shall be selected to trip or shall be rated at no more than the following percentage of the motor nameplate full load current rating. Now, again, don't be misled here. Nameplate is full load amps, and it might be FLA on the nameplate. The full load current is typically what you see in the 430.248 table we looked at, which is the back of the book. That's in 430.248. That's the full load current. So this is probably full load amps. But because it says nameplate, you're simply going to pull from the nameplate. So don't let that cause any confusion. Now, we're sizing this overload. We have 3 conditions here. Now, if the motor is marked with a service factor of 1.15 or greater, then we size it at 125%. If the motor has a marked temperature rating of 40 degrees C or less, okay, then we do it at 125%. If it's all other motors that have neither one of these markings or these conditions apply, then you do it at 115%. Okay? All right, so that's the basic that we're going to follow, okay? All right, now, it goes on to say where now just before we add it up, it says, now, keep these things in mind. It says where a separate motor overload device is connected so that it does not carry the total current designated on the motor nameplate, such as for a wide delta starting, the proper percentage of the nameplate current applying to the selection or setting of the overload device shall be clearly designated on the equipment, or the manufacturer's selection table shall take this into account. Okay, so if this is the condition, it needs to give you that in an exam. Okay, so come back to it. So that's why we say follow the basic general rules, whether they give you service factors, rate of rise, all those are the basic things they'll give you in an exam. There's not enough time and usually for them to give you all of these manufacturer information unless they flat out tell you this. And if it does, you follow the procedures that they tell you for it. You follow the rules because they have to give it to you. But the basic rules, we're talking about basic exam prep to kind of move you through these calculations, is to simply look and determine what you're dealing with. What is a service factor? If no service factor is considered, then you don't consider it. If it's not on there, you don't consider it. Okay? Don't overthink it. Don't try to add something in there that's not there. If it doesn't give you the motor rate of rise, then don't assume it. It's not there. And sometimes the basic calculations won't even give you that. Okay? Again, like if it doesn't ask you about voltage drop or give you any conditions, don't assume it. Okay? You don't have to worry about that. Don't overthink it. Okay? All right, so let's get back. All right, so let's get back to the code. All right? So that's what we're going to deal with now. Now, what if, and I should look back here, that's for your separate overload device. All right, and I'm going to give, now, let's go into a different, you see it keeps on going, and then you have C here. Oh, hold on, here. Okay, now it says, now, let me read you this one. It says, where the sensing element or setting or sizing for the overload device selected in accordance with 430.32A1 and 430.32B1, okay, is not sufficient to start the motor, I don't know why it keeps doing that, sorry, to carry the load, a higher sizing sensing element to increase the settings or sizing shall be permitted to be used, provided the trip currents of the overload device does not exceed the following percentage of the motor nameplate full load current rating. Okay, so the rule of thumb, that we're not going to talk about thermal protectors, okay, on this one right here. Again, you would simply pull this, but that's generally not what we're going to run into, and all the same basic rules apply, and we can't cover everything. We're talking about, look, let's come back to me so I can make this really clear. You had your rules for the service factor dealing with it, or the temperature rise. You deal with that, whether it's 125%, or if there's none of those and all other motors that don't tell you anything, then use 115% if it just doesn't add. It says, what's the overloads for this, and doesn't give you service factor and rise. If this question states that after you apply the overload, it doesn't hold, then you're able to go to this table. If it can't handle the starting current for the overload, if the overload can't handle the starting, then you can go to these values and use these values. So you always start at the first aspect, then you can go to the second if they tell you that it can't hold. All right? So and that's kind of how questions work. So let's go to the code again and we'll kind of really narrow that down. So here's what you do first. So you're going to use 430.32A1, because in our case, we're dealing with a separate overload device. And this is what you're going to do based on these variables you give here. Now, it reminds you and says, okay, it doesn't hold, okay, then if that's the case, you still have the service factors or the rate of rise that comes into play. But because it wouldn't hold, you can use 140% or even 130 on all other motors if it doesn't hold, okay? Remember that. You start with this one here. And if you had your code book and you're highlighting it, I would highlight this one. Highlight the fact that it says this application here, continuous duty motors, and then separate overload device. and then highlight these here, as well as service factor and then temperature rise. Those are the kind of things that I would highlight to call that out. So let's do this. Let's go back and look at our graphic and see what we're actually asking. So in our graphic, it says, okay, size this overload. We already know the FLC, but we need to know the FLA on the nameplate. Well, here's our nameplate information. Now, exam question might give it to you. It says the nameplate FLA is 24 amperes. It says the service factor is, and I'm sorry about the both, that's used later in another calculation, but only have one right here. So it's 1.16 service factor. And it says the temperature rise is 40 degrees C. Again, this is for use when I have more than one motor, so ignore the both here. But that's what the actual values are for this motor. And again, thermal protection or thermal protector is not integral. So that's why we're using a separate one. And the motors are considered a continuous duty. And that's the kind of information they're going to give you on the exam. Otherwise, you assume it is. Don't assume anything unless they give you, except for the basic rules. In the basic rules, all motors considered continuous duties state lest they state otherwise. Or they'll tell you that in the exam question. Okay? All right, so let's size this overload. And we got more graphics we're going to use, but we're going to move through it really quickly. But this is just the basics of the single motor, which is going to really help you for the other aspects. All right, so now let's go back to the code again and let's select it. So it was 116 service factor and temperature rise was 40. All right, so let's go back to the code and see which one we have to choose. All right, so with motor factor 115 or greater, it's 125%. And it says motors with a marked temperature rating of 40C or less. With ours was 40, so it's still 125. So the value is 125, and that's what we're going to use. So let's come back to me and do our, well, actually, let's go to the PowerPoint one more time. And look, okay, so we've got 24 amps. So we're going to take the 24 amps, which is our FLA, and we're going to take 24 times 1.25, and that is 30 amps. Okay, so let's come back to me. So the 24 amps was the FLA from the nameplate. So remember, overloads, look at the nameplate, not the FLC. Hammer that in your brain. Most everything else, you're going to use the FLC. And the reason is that's a standardized table for future motor replacement. If you always go to that table and you realize that a 5 horsepower motor, single phase at 230 volts, you can use that value. Even if there's some differences in motors, they use that. You get to the basic standards and it keeps you in line for servicing, replacement. That's the standardized table that we use. Now, engineers will say otherwise. If there's all these variables, you're an electrician, you're preparing for an exam, this is what you're taking into account. Okay, don't overthink it. All right, so breathe and relax. That's all you got to do. So 24 was the FLA times 1.25, 30 amperes. That's what we got. So the overload is 30 amperes. So let's go back to the graphic. So in this case, we have conductors, 10 gauge. In our case, inverse time, which is a 70 amp. Yes, 70 amp is protecting these conductors from short circuit and ground fault protection. The overload is protecting it from overload at 30 amperes, okay? Because that is the actual running of the actual motor, and it's not going to overheat it. It's perfectly fine. The rules that were found in 240.4 for small conductors don't apply because we had the allowances of 240.4G, which says that we could use it. We know that our terminals are rated at 75. So that was why we went in the 75 degree column. Remember that if the conductors were 6 degree rated, that's the weakest link, that would have bumped us up to an 8. So just keep that in mind. That's important to understand 110.14c. And so now we have sized this entire circuit. 30 amp overload, 70 amp overcurrent device, 10 gauge copper. We're going to assume here, because it's 7575, we used THHN, THWN-2, or we could have used THW if we wanted. That's 75 degree rated conductors. So for an exam, don't take into account ambience. So let's come back to me and let's do a recap, and then we'll run through the other ones pretty quick. Don't assume anything at all. Take your calculations as they are. Don't assume ambience. Don't assume number of current carrying conductors in 31015B. All those aspects. Don't get into that. Only answer what's in the question and slow down and read the question. If it says exceptions excluded, then you know, for example, you can't use the exceptions. that gets a lot of people. In fact, the examples I put online that people were getting all wrong on LinkedIn were basically based on the fact that they didn't read the last line and it said exceptions excluded. You can't use them. In most exams, you're okay with the exceptions unless they state otherwise. Just remember, you can't go to the next size up if the exception is not used in many of these cases. That means you'd have to go down. Okay. All right. So let's move on to the next graphic because I think we've got that covered, and we'll just kind of hash it out in the other ones. All right. So we're in the graphic PowerPoint. Let's go to the next one. All right. So in the next one here, we've got multiple motors that we're dealing with, and we already sized this one, and we know how to size these. Okay. So now we need to size how we size this feeder. Now this feeder has to handle both of these loads here. Okay. And we're not going to have all the answers here in the code. We're just going to kind of run you through it because you saw how to size each one. So we have to do that. So we did it for this one. But here's the interesting thing about the feeder circuit here. This is a feeder and it's feeder, and these are considered tap conductors, and they're covered under 430.28. And we'll look at that in a slide in a little while. And so, again, we're doing simple single-phase application here. And so, in this one here, we're going to say, well, how do you size this? So, where do we go for this? Well, you're going to go to 430.24 because this is dealing with the feeder. So, let's go to the code and see what it says about the feeders. So, we want to go to 430.24. And you know that because, oh, I went too far. Let's go back. In fact, I'll just do this here because I get a lot of complaints from people that say, why don't you use the search feature, Paul? And I'm like, because I don't want to. All right, so let's go here. It's 230.24 right here. Now, notice it says we have servo motors or motors and other loads. And in our case here, again, we're not talking about remote. We're talking about just the motor, very basic, unless it tells us otherwise. Okay. And just to show you what this is under, this is falling under. Here you have, again, for the single motor, and then you come down and you're dealing with servo motors. Okay. So it says conductors supplying servo motors or motors with other loads shall have an ampacity not less than the sum of each of the following. Okay, so the first one says, okay, look, I got to take 125% of the FLC rating of the highest rated motor as determined in 430.6a, okay, which is basically telling us, again, in that motor. Now, if you want to see what that says in 430.6a, because some people say, well, show us that again, and I will. 430.6. We want to cover everything. So 430.6a here is basically telling us to use the tables, and these are the tables, in order to get the FLC. Okay, that's basically what it's really telling you. All right, so let's go back to where I was. Give me a second while this. Okay. All right. So we got servo motors that we're involved with. So 125% of the full load current for the highest rated motor. And then, of course, the next one would be the sum of the full load current ratings of all other motors in the group. And in our three-phase, you're going to see that one's pretty interesting because we're going to show you how to do a group application, because you could have single-phase and three-phase all on the same feeder and taps. And it gets kind of interesting. But we're just dealing with single phase. So let's kind of go back to our graphic and establish something. All right, so we've already done this one. We knew that this was 28 amps as FLC. We've sized all this. And at this point right now, we don't even need to know this other stuff to size this. We just need to know what the FLC was, or the largest one. Well, this is 5 and this is 3, so you know this is going to be the largest one. But we still need to know what the FLC of this 3 horsepower motor. So as you probably guessed, where are you going to go? We're going to go to table 430.248. So let's do that now. Let's go to that table and find out what that is. So let's go in our code book, and you're probably going to have a tab for that if you're taking your exam. I definitely encourage you to tab. If you don't have a tab, just be familiar with these things are in the code. because I'm understanding that some test sites won't let you use your tabbed out book, and I think that's just too sneaky by the testing authority. Why would you not? You're expected to have a code book. Anyway, let's go to 248, and I'm going to keep going until I get there. Oh, I went too far. All right, so here we go. So now we're looking at the three-phase. So here's our three-phase and a 17 amperes. Okay, so now let's come back to the graphic. So we know that there's 28 you see here for the 5 horsepower, and then we need 17. So let's come back to the graphic. So in this case, it's 28 here, 17 here. It said take 125% of the largest plus the sum of the FLC of the other. So in our case, we did, and let's come back to me, and we'll do our little calculations. So we're sizing this conductor, this feeder, if you will. So it was 28 times 1.25, it's 35 amperes. And then we're going to add the sum of the other motor, which is a smaller motor. And that was 17. So it's 35 plus 17. That is 52 amperes. Remembering all of the sizing rules and the allowances that we can utilize the values in the 31015B16. We don't have to worry about small conductor rules, although this is larger than small conductors that we're looking for. Just keeping that in mind. Again, remember terminal limitations. We're technically under the 100, so if you didn't have any markings, then you'd still be in the 60 degree. Okay, but in our case, we told you that it was 75 degree rated terminals. Okay, and we're going to know that the motor's terminals are probably 75, although there's no motor termination here. For this conductor, there's still the breaker termination. So in our aspect here, we are going to utilize, because we want to use a conductor that's rated 75 amperes to take advantage of that higher ampacity value. And it might even be a 90 degree rated insulation. But again, because of the terminal limitations and because of the rules, we might use a 90 for adjustment and corrections, and that's in our demystified D-rating series. But here, we're going to stay in the 75 degree column. That's our weakest link. And we're going to choose those conductors. Now, again, if an exam gave you a TW or didn't give you any wire type, and you know that it's under 100 amps, you know that you're going to default into the 60 degree temperature rating of 31015B16. Just kind of things you got to remember. Hey, being an electrician is complicated. Dang, that's why we get paid the big bucks, right? I hear you. So let's go back to the code and see what we're talking about. So, because I need a conductor that's good for 52 amps under the terminal limitations, 75 degrees C in our condition. So I'm going to go back to the code. And, all right, so I've all done this. So now I want to go to 310.15B16. You should have a tab for this. If you don't have a tab for it, you might want to consider one. All right, so here we know that the terminal limitations are what? 75 degrees C. We use any of these conductors, or remember, in accordance with 110.14, we can use any of these conductors, but we're still limited to the termination limitations of our question in our exam. Now, again, if it was no conductor type listed, it just says what size conductor, and it tells you assume copper, and it didn't tell you that it was 75 degrees C, you don't assume anything, then you would be in the 60 degree column. Remember that. It's so important for you to remember 110.14C terminal limitations. All right, in our case, we are dealing with 75 degrees C, so we had 52 amperes. So could I use an 8 gauge? Well, obviously not. It's only good for 50. So I would have to use a 6 gauge, and that's what I'm dealing with. Again, if the question asks you about aluminum, then it's simply the same scenario here. It would be a 4 gauge aluminum under the same condition. All right, so it's just that simple, and that's how you would size it. So let's come back to the graphic, and under the graphic, these conductors here are going to be sized based on the FLC at 125%. Again, don't assume anything unless they tell you otherwise. And then it's going to be 100% of the FLC sum of this motor, which was 17 amperes. And again, that's to be the size of this conductor here. All right. Now, again, sizing these, you do the same way we did before. Okay. And we'll do that at the overall question at the end. Now, We're going to size them. Actually, we're going to do it right now. So how do I size these two? Well, this one's already done. We know that that's a 70, okay? Because that's what we've inverse time. We already did it. We already know that these conductors here are all based on being a 10 gauge. What about this one? Well, this was 17 FLC. Well, we know here if it's a circuit breaker inverse trip like we asked here, then it's at 250%. We already established that. We already looked it up. We know where that is in the code. 430.52, we looked at the table. We determined it was inverse time. If it was one of the other types of fuses, you use that percentage. But what we've got is 17 times 2.50, and that's 42.5 amps. Okay, for this one. Now, let's make something really clear, and I'll come back to me. If it said exceptions don't apply, because we know that there isn't an overcurrent protected device, or I should say on that table, the standard sizes, there isn't one that's 42.5. There's a 40 and then there's a 45. Because one doesn't correspond and the exceptions apply, I would be able to go up to the 45 and you're still okay. If the rule said that exceptions do not apply, keep in mind that I can't exceed the 250%. So I couldn't go beyond that. I'd have to go back to the 40. Okay, watch that. On an exam, they might state that, and then you'll be given, obviously, you know they're going to give you 45 amps as an example. They're going to give you a 42, they're going to give you the 42.5, they're going to give you the 45, they're going to give you the 50, and they're going to give you a 40. If the exceptions don't apply, then you know it's the 40. If the exceptions apply, then you know it's going to be the 45 if you're dealing with this 42.5 amp application, okay? So if you go back and look at 240.6a, you'll notice that there isn't a 42.5 breaker, and that should make common sense because it's the 0.5. Then, if exceptions apply, it's a 45. If in my example on the LinkedIn, and in this example here, you note that it says the exceptions don't apply. Then that means that this overcurrent device had to be a 40, or this short circuit ground fault protection needs to be a 40. That's not a trick. It's just kind of making you understand the exceptions. So let's go back to the presentation. So see, exceptions not considered. So the first mistake people would think is, oh, then you could do that. 40. Now this one was 70, no exception needed to be because there was a breaker. But this one, if you use the exception, then it would be up to 45, but no exceptions can apply, so it's a 40. Now, overload, same scenarios apply, the same as we did before, but we're not asking that in this example right here. But you would be the same as it was in the other. Then you're generally going to apply 125% to the FLA, which is the nameplate rating, and that's how you size this one. So this one was 30 amps, and this one, let's just do it for just to say what it would be. And basically, let's say the FLA on this one, let's just say, throw it out on a limb and say it was 18 amps. I'm just throwing one out there. If the FLA was, I'm just throwing it out there. If the FLA was 18 amps on this one, then it would be 18 times 1.25 because of the service factor was 1.16, okay? And the temperature rise was 40 degrees C. So that means 22.5, okay? So I have to have an overload that it's at least 22.5 amps, okay, for that overload protection, okay? At least that, all right? So typically on that, I typically would go to an overload that doesn't exceed those values of that. So let's go to the code and to select that since we're already here. Let me get a search box up. And that one would be, again, is 430.32. I like doing this, and it does eat up time, but I like to go through each of these things because I want to make sure that you all understand it. So here's the motor. It says each motor used in this whenever are protecting against overload by one of the means. And we were using, in our example here, and it says, shall be rated no more than the following percentage of the motor nameplate rating. In this case, it was 22.5, then it would be a 20 amp rated, okay? Now, again, if that doesn't carry it because of the sizing, then you're allowed to go up higher here, okay? So that would be the minimum. But let's say it wouldn't carry it. This 22.5 is what we came out with, and it sized at 20. So what if it doesn't carry it? And that was in your question. So then you take I think it was 18 times 1.25. Yes, so it's 18. It was the FLA. So it would be 18 times 1.40. And that'd be 25.2. So that would be a 25 amp rated for that. Okay. All right. So this kind of gives you an understanding of how that thing, but you're not to exceed the percentages of the nameplate full load current. Just don't let the exam fool you. Just read it and read those important little statements that says not to exceed, and look for whether or not an exception applies that you can exceed something. Okay. We're dealing with the overload protection here, so follow it and read the code. All right, so let's go back to the presentation. So that's how we would have sized that. So in this case, this would have been, depending on the condition, this right here would have been either a 20, and if it didn't hold, it could go all the way up to a 25. All right. Now this is kind of asking you everything. Now that we just did these two, so this one's taken care of. We just sized these two. And again, we didn't really size this one, but it would be the same as we did for this conductor here, this taps here. And this would be in this case, it would be, and you see my example, actually the nameplate was 16 amps. So actually we would have done it at 16 amps for this one right here. So I kind of guessed on the other one. All right. So we're kind of going to, let's do all this really quickly. So we already sized this. We knew this was a 6 gauge based on 125% of this FLC plus the sum of this one. Sized this. That was good. We sized this one at 70 amperes. We sized this one here. We did this calculation, and it was the inverse trip was based on the FLC. I don't know if we actually sized it. So this one was the FLC was what was the FLC on this one? Here, we got to go back and look. Let's see what the FLC is on the 3-phase motor. I can't remember. So let's go back to the code. You would say, Paul, why don't you remember that? I'm sorry, I don't remember it. I want to think it was 17. Oh, it was 17. I'm sorry. Let's go back. I don't even need to do that. Let's go back. So it was 17. So the FLC on this one was 17. So in order to size this, it says it's 250% because that's what we got at 430.52 in the table based on what we got here, just a continuous duty motor, non-torquing, so we don't have to worry about the aspects of a torque motor or high torque or even a low torque motor. We're dealing with this. So it is, again, we're following the basics. Don't overthink this. If you're sitting out there going, he didn't talk about every single condition, dude, that's because this is the basics of what you need to know. Okay, I can't help it if you're a genius. Most people need to do the basics first, all right? All right, so it was 17 times 2.50, and that's 42.5, and we said that this cannot exceed that unless the exceptions applies, and here it says exceptions not considered, so this would be a 40 ampere. So this was a 70, and this was a 40, okay? So we sized this based on the FLC 17, which was the 17 times 1.25, okay, which is just like we did this one when it resulted in a 10. So 17 times 1.25, and that equals 21.25 amperes. Okay, so what size would that be? Considering, again, all the conditions are the same, 75-degree rated terminals. Again, if it doesn't state the type of wire type because of the ampacity and the size, you know that it's going to be 60-degree column. If it says TW, you know that's in the 60-degree column, regardless of the terminal limitations. If it tells you it's THHN and you see the terminals are 75, then you're going to stay in the 75-degree column. All of this is in accordance with 110.14c. Again, I am repetitive because I go so quickly. I want to hammer these things in your head. All right. So now we have to size that conductor for 21.25 amps. And I think most of you out there know that it's going to be a 12 gauge. But let's go to that real quick. So it's 310.15 because I want to see what you're dealing with here. 310.15B16. Incidentally, I don't know if I told you before, that is actually going to change in the 2020 code. It really looks like it's going to all go back to 310.16, but you know, we'll see what happens. All right, so here we need a conductor, again, 75 degree, because we know that the terminals are rated at that. Again, if it was a TW or it didn't give any rating due to the ampacities and limitations in 110.14c, I'd be in this column. And that means that conductor would have to be a 10 because 12 is only good for 20. However, since with 75 and we're going to assume that it's either 9-degree insulation, but we're limited to the 75 terminals, we're going to choose from the 75 column. And we didn't get anybody ask us about adjustment or corrections or any other variables that are in 310.15. So, in this case, I have a 12 gauge. It's good for 25 amps. Can that handle the 21.25 amps? Most certainly it can. Under these terminal limitations, it has no problems to do that. All right, so let's come back to me. And so we've sized it and we know what we need. We have a 40 amp overcurrent device for this 3 horsepower motor at 230 volts based on exceptions not applying. So it's a 40 amps short circuit ground fault protection. The conductors itself are rated for a 12 gauge because they're good for 25 amps, and the actual 125% of the FLC was 17 amps plus 125%, so that pushed us that. So we're good there because that was what, 21.25 amps, and we used the 12 gauge. We're good there. Again, those small conductor rules don't apply with the motors. Keep that in mind. Your mind wants to think, oh, I can't do this because I can't have that. I can't have a 40 amp device with 12 gauge conductors. And yes, you can when you're dealing with motors. You can also for HVAC applications and other things that are in the code. All of those listed in those allowances in 240.4G modify the applications for overcurrent protection. In this case, the rules we're using are for short circuit ground fault protection, which sends us back to that overcurrent protective aspect. You get what I'm saying? All right, so we're following that. And let's go back to the presentation and see if we've covered everything for it. Oh, the overload. We already know the overload was 20 amperes. Unless it didn't hold, then it could be 25, rated for 25, okay? Or if you can follow the manufacturer specifications for that overload if they're provided. Otherwise, you use the code, and that's how you size it, all right? In an exam, they're going to give you the values because they're not going to assume any manufacturer information because there's so many different manufacturers. They want you to answer the question, okay? So keep that in mind. All right, let's go back to the PowerPoint. So we've sized all this. The only thing we haven't sized yet, okay, is this breaker. This breaker protecting this feeder. How do you size it? Well, how do we size the feeder to this application here? We know the conductors are 6 gauge. But we have rules that allow the same aspect that we have here, that this can actually be sized larger than what would be typically required for these conductors. And where do we go for that? Let's go to the NEC and determine what we do with that. So what we're going to do is do a search now, and I believe it's going to be for sizing that device. And hold on here, let's see which one. We're going to look at 430.62, and I want to get to 62, and I'm going to do this and do a search for it. Now you're saying, how did you know to do that? Well, you remember we talked about for feeders, it had that protection there. Well, see, part 5 is dealing with motor feeders short circuit and ground fault protection. And don't worry, it's going to send us back to 430.52 for our work kind of values, but you just kind of want to follow it. All right. So what does it say? General. It says part 5 specifies protective device intended to protect feeder conductors supplying motors against overcurrents due to short circuit and grounds. Probably should say, it's kind of a typo there. I don't think we even corrected that in the 2020. It should for short circuits and ground faults. Okay. Kind of probably should. Somebody should submit a public input for the 2020 to correct that. I think it's too late now. All right. So let's do that. So here's what it says. The feeder supplying a specific fixed motor load and consisting of conductor sizes that are based on 430.24, which we already did, shall be provided with a protective device having a rating or setting not greater, remember that, not greater than the largest rating or setting of the branch circuit, short circuit, ground fault protective device for any motor supplied by the feeder. So that's the larger. Okay, and that is based on the maximum permitted value as specified type and that was based on, again, for our example, is 250% in 430.52. So that's what I was kind of talking about. All right. And again, if you're dealing with hermetic refrigerant motors, then you'll refer to 440.22a, but we're not going to apply here. We'll talk about it in a different video. And then it says, plus the sum of the full load currents of the other motors of the group. So let's go back and see what we're talking about here. So let's go back to the PowerPoint. So we know that this one was rated at 70 amperes because that's the larger of the two. And then we know the FLC of this motor is 17 amperes. So really all it's asking you to do is take this value that we've already calculated before. That's why it's so important to know how to do the single ones here. And this was 70 amperes. Then you simply add the 17 amps to that. So you get your trusty calculator out, and I'm going to do that. And in your exam, hopefully you bring a calculator. And so it was 70 plus 17. It's 87 amperes. Now, remember when it said not greater? It can exceed 87 amperes. So, no exceptions apply, even if there was any. We're going to say here that the code says you can't exceed it. Now, we're going to look at it a little closer, but it says you can't exceed it. So now let's go back and look at the code and see if there are any exceptions to that, because that's the next question people say. Because you had one when you're protecting the single conductors, but did you have one for the feeder? And let's look back at it. So let's go back to the code. So the code gives this basic rule, all right? And there is an exception. But this is dealing with instantaneous trip, which we're not going to cover in here because I've already gone quite a long amount of time. And its exception 2 allows an allowance when the feeder overcurrent protective device also provides overcurrent protection for the motor control center. And of course, those are rules that are covered in 430.94. Okay, that's just allowing you an exception to this rule here, saying you can't be larger. Okay, if that exception applies. Generally, they're not going to do that on an exam, but just be aware. Okay, other installations. It says, just to cover it, it says where feeder conductors have an ampacity greater than required by 430.24, the rating or setting of the feeder overcurrent device, a protected device, shall be permitted to be based on the ampacity of the feeder conductors. Now, what does that mean? So in an exam, you're going to size it based on the values like we did. These are what the rules are. If they arbitrarily gave you feeder conductors that were much larger than necessary, then that overcurrent device that's protecting, or that breaker, for example, protecting that feeder could be larger. Because remember, your motor has its own ground fault and short circuit protection there that you're going to size accordingly. But this is for the feeder. So if it's a bigger feeder, and it's larger than necessary, then that device, that exception allows you to size that overcurrent based on protecting the ampacity of what that conductor, those feeders can carry. So that's what that exception is about. Don't assume that. That's not typically a question they're going to give you on an exam. They want you to follow the basic minimums of the code. Now, will it ever potentially show up? It might, but I need you to be aware of that. But generally, you just follow the minimums, because we want to make sure you know how to use the code. We're not trying to trick you here. We're just trying to make sure you understand the minimums of the code, okay? And I'll be honest with you, if it went all into that detail and started to go in where you got to go here, there, skip it. There's too many other ones in there. They're going to get you past your test, okay? That's too convoluted of a question. They're basically going to do the basic parameters that we're talking about right here, okay? So let's go back to the actual code. So in our case here, we're not dealing with that. We're just simply saying, look, let's go back to the rule. We're going to base it like I just sized it. So we said it was 87 amperes. And I don't see anything. It says not greater than. So now I have to go to 240.6a and see what that standard breaker is going to be. Now, it was 87, I believe was 87. Well, there's an 80 and there's a 90. Well, I can't go to a 90 because it says not greater than 87. Now, here's a case where if a manufacturer made an 85, then I could use an 85. But because I'm using standard size, and they're permitted to do that if they make one. But in this case, it would be an 80. So in our question, let's go back to the PowerPoint. In our equation, this would be an 80. So we have an 80 protecting a 6 gauge, copper in our case, copper, with, in this case, 10 gauge conductors with a 70 amp short circuit and ground fault protective device here, which is actually the overcurrent device specified in 240.6a. And the overload at 30 amperes, all with 10 gauge conductors, and it's perfectly okay. And of course, we already went over this. All right, so that is how you solve all of these basic equations for an exam. You don't assume anything. You solve for what's given. You pay special attention to exceptions. You pay special attention to the terminals. They might trick you by giving you, well, it's not a trick, but they might say everything's rated 75, but the wire they tell you to use is TW. Then you got to know you're in the 60. They might tell you nothing as far as terminations, but based on the ampacity, since it's under 100 amperes, or 100 amperes or less, then you know that you're going to be default into the 60-degree column for ampacity. So just don't be fooled by all that. Make sure you watch our derating demystified, or even listen to my podcast that talks about 110.14c. So if you haven't listened to that podcast, go over and listen to it. But part of your study prep in this series is simply to talk about basic motor calculations. And these are generally all the basic motor calculations you're going to need to get by your exam. So the next question I want to ask you is, do you know what these conductors are right here? Okay, in the first graphic that we show, and I'm going to go back to it real quick, this one. These are single motor conductors. These are branch circuits dealing out, and this is all basically mirrors branch circuits and all this kind of stuff right here because it's from the overcurrent device out the branch circuit, and then these are pretty much considered single motor conductors, and basically it's all sized the same way, 125% of the FLC. That's pretty easy. Now you're going to pretty much, let's go back to where I was. You're pretty much going to size these the same way, but you do have some limitations that you need to be aware of, and they're going to be found in 430.28, and I just want to make you aware of these, and it should take care of itself, but as a code learner, you want to keep these things in mind. Now, these are called tap conductors, okay, because they are tapping a feeder, okay? These aren't called branch circuit conductors because they're not from an overcurrent protected device to the outlet. I mean, these are not connected to an overcurrent device. They are tap conductors. Now, you're typically not going to use the tap rules in 240.21 and things like that because those are feeder taps. And you're really going to try to stay for your code. You're going to really kind of stay in 430. I just don't want you to get lost in other aspects. I'm trying to keep this very simple. So let's go to 430.28 of the code and just kind of look it over. So I'm going to type here 430.28, and this, not necessarily you need a tab, but you do want to tab all these things, but you don't really need a tab for this. All right, so here's what we're talking about. When it deals with motors, we're dealing with a feeder tap. What is a feeder tap? Feeder tap conductors shall have an ampacity not less than. Now, we've already calculated ours, okay, those tap conductors, 10 gauge and 12 gauge. We kind of, that required part 2. Well, that was the part we just did. So we know a 10 and 12 were our conductors that we were using from the feeder down to the motor. All right, it says, and they shall terminate in a branch circuit protective device. And they do in our example. It is still considered, and let's go back to the graphic, these are considered branch circuit protective devices, but they also are, again, providing short circuit and ground fault protection. So you just kind of got to know that. That's what they are, okay? All right, let's go back to the code. And in addition now, shall meet one of the following requirements. So we sized it based on part 2, and then it says, okay, look, one of the following. It says, all right, look, man, it says be enclosed either by an enclosed controller, okay, or by a raceway not more than 10 feet in length, and for field installations be protected by an overcurrent device on the line side of the tap conductors, okay, and rated or settings of which shall not exceed 1000% of the tap conductor's ampacity, okay. So this is one condition if you want to meet all of these rules, okay. But it says any one of the following. So what about 2? 2 says, okay, have an ampacity of at least 1/3 that of the feeder conductors, be suitably protected from physical damage, ours are in a raceway, and not more than 25 feet in length. Well, let's see if that one's the one we're applying here. So let's come back to me. So it's 1/3, okay? All right, so let's come back to me. Okay, so we had this 6 gauge, right? And we determined the 6 gauge. So it says, what's the ampacity of that 6 gauge? Shall have at least 1/3 the feeder conductor, have an ampacity of at least 1/3 of the feeder conductors. All right, so we said they were 6 gauge. So what we want to do is now we want to go get what is the ampacity of that 6 gauge conductor, okay? So let's go to the code just to see what we're dealing with. And I'm going to go to the code and we're going to go back to 310.15 B16 to do this. And here we are. And that 6 gauge was 65 amperes. Okay, so 65 amperes divided by 3 is 21 amperes. Well, in our case, the 10, okay, so it can't be less than. So in our case, we have a 10, which is good for 35 amperes. Well, that's more than 21, so it's definitely more than 1/3. So let's go back to the equation. So we're still looking at the code. Let's go now. We already know what we're there. So we know that a 10 is good for 35 amps, and incidentally, a 12 is good for 25. All right. So let's go back to 430 dot. Where were we at? Where did I want to go? Forgot where I was at. I can't remember where I was. Oh, 28. There we go. Okay, so we're going to 430. So here we're back here. Make sure that y'all are still on it because sometimes I lose the screen. And it says this one. It says shall have an ampacity of at least 1/3 of the feeder conductors. Well, 1/3 is 21. So both of those 12 and that 10 comply to this rule. And as long as it's not more than 25 feet. And incidentally, the third one just says shall have an ampacity not less than the feeder conductor. So I could have used those taps could have been 6 gauge all the way down, and that would have been okay as well, and I wouldn't have to worry about anything or if I wanted to do that. But most of the time, that's not what comes into play. You do have some allowances here for feeder taps that are longer than 25 feet, if that applies, and you have all these rules here, but we don't want to get into that as far as the basic rules. Okay, so let's go back to the presentation and see if we covered everything. So we covered that. Let's see that. Boom. That takes us back. So let's come back to me. All right. So what have we done? We have sized every component, the basics, for single phase. We sized the feeder's protective device that's protecting the feeder conductor. We sized the conductors. We verified that those tap conductors were at least 1/3, and that's the rule we used. In our case, they were in raceways. And they still were sized in accordance with Part 2, so kind of see how that rule works out. We did all that. We had the different allowances that we could have used, one of the 3 for those conductors that would have got us there. We sized the overloads. We sized the short circuit ground fault protection at the actual circuit breakers. we saw that the feeder overcurrent device could be larger if the conductors were larger on those feeders for whatever reason. So we took all those things into account, and that's the basics. Can it get more complicated than that? Sure. We could have conductors that after you choose the right conductor size that you need to handle the load, then, and only then, do you then have to consider applying things like adjustment or corrections. The adjustment in accordance with 31015B2A or B3A, or the ambient adjustments in accordance with 31015B2A, if they come into play. Remember everything about 110.14c. Watch that video as part of this prep series. This video is part of your exam prep module, is covering simply single-phase motors. Now, I will remind you, all of this is the same basically when we go into three-phase. But then we'll have different groups on A, B, and C, and you need to find the largest motor on the different groups and balance things out, and a little more complicated. And that'll be covered in the three-phase motor basics, which is another module in your exam prep series. So hopefully you got something out of it. If you have any questions, remember, you can email me at any time here at Electrical Code Academy. It's just info, that's INFO, at electricalcodeacademy.com, or for short, you can email me at info, that's INFO, at masterthenec.com, and I'll answer your emails. Don't forget to visit our Facebook page. We have an exam prep forum that is a closed group. So you've got your open open Facebook page, and then you can request to join our closed forum where I provide a lot of extra information to help you prepare for an exam. So this is just one module in your exam prep component, and hopefully you found something out about it that really you didn't know, or that you learned something. Maybe you're a seasoned code guy and this was the old hat for you. But again, this is for that apprentice and that journeyman studying to take the next level. And this is the basics, okay? The basics of motor circuitry, okay? When it comes to overload sizing, short circuit ground fault, whether it's fuses or circuit breakers, really just stop and study what the question's giving you. Understand whether the exceptions apply or they don't apply. All of those values. Understand whether or not the exceptions are going to apply, that you apply them. If they're not, ignore them. Understand those conductor limitations. Okay, everything might say 75 degree, but the conductor they tell you to use is a TW, and you got to know that it's 60 degree. Keep those things in mind. That way you don't make a mistake on your exam. So hopefully you got something out of it. Hopefully this is just one module in a series here that you start to learn the code a little better. So hang in there. You'll pass that exam. If you have any other questions, reach out to us and we'll be glad to help you any way we can.